Okay, so remember last time? Okay. So remember in our last set of notes, we went over some of our guidelines, kind of like what we should look for. So remember with our proving trig identities, none of them are the same. So it's not like I have like this rule or these steps and this is what I'm gonna follow every single time. But remember we did talk about that there are some like techniques that we can look at using that might help us. And we kind of looked at a few of the more simple ones last time, but we're gonna look at a couple of the other guidelines today. So for our first question, it asks us to verify tangent of x plus cotangent of x equals secant times cosecant. So remember that our first guideline was that we always want to start with the more complicated side. So in this case, which side might be the more complicated side? Maybe the right. Why do we say the right side? So they both have two trig functions, and they both only have one operation. So there's not like a right or wrong answer. However, I will tell you that usually if I have addition, it's going to be easier to combine things than it is if I have multiplication and try and break those things apart. Does that make sense? So usually if I have addition or subtraction, that's usually going to be the side that I start with. So if we start with our left side, so remember that a couple of our guidelines, one was to factor. Well, is there anything that I can factor out from those two? Do they both have anything the same? No, right? Because they don't both have like a sign multiplied to it or a 2 multiplied to it or anything like that. So I can't factor anything. Then we also said that we can multiply, but we don't have multiplication here. And then our next one was that we could find a common denominator and add or subtract. Well, I have addition, but we don't have fractions. So we can't find a common denominator. But what was one of our other guidelines? Here. The second one. Convert everything to sines and cosines. Now, is there a way that I can convert both tangent and cotangent to sines and cosines?
Sine over cosine, cosine over sine.
And what are those called?
Quotient.
Your quotient identities. And the nice thing is, once we do that, notice we get fractions. And so then, what can we do with those fractions? Find a common denominator and add them. So, what do I need to multiply my first fraction by? Sine over sine. So I get sine squared of x divided by sine of x times cosine of x. And then what do we need to multiply our second fraction by? Cosine. So we get cosine squared of x divided by sine times cosine. So then notice we can combine those. And what do we notice about our numerator?
It's one of our Pythagorean identities.
It is. Anytime that I have something that's squared, I'm going to try and see if I can use my Pythagorean identities. Squared things are usually a good idea to look and see if we can use our Pythagorean identities. And in this case we can, because what is sine squared plus cosine squared equal?
1.
1. Well, that's nice. Well, now I have 1 divided by sine times cosine. So do I have a trig identity that has fractions with sine and cosine in it?
What is 1 over each?
And what are those called?
Reciprocal identity.
The reciprocal identities. So what is 1 over sine?
Cosecant.
Cosecant. and 1 over cosine?
Secant.
Secant. And this is multiplication, so just like 2 times 3 is 6 and 3 times 2 is 6, I can switch my order and we get what we wanted to have. And then remember, we want to write out our concluding statement. So we would say, therefore, tangent of x plus cotangent of x equals secant of x times cosecant of x. And the question on that. Alright, so now on our next one, what do we want to do? Which side do we want to start?
The right side.
The right side? Okay. So notice this time we have addition and subtraction in both of them, so that's not really going to be anything. But we do have a fraction in our right side, which means that might be a good place to start. So if I write out my right side, so I have cosine of y divided by 1 minus sine of y, what do we want to do?
I would do cosine over 1 minus cosine over 1.
Be careful. So let's think about if I had 2 divided by 22, right? And I rewrote this as, okay, could I do that and say that that's 1 over 20?
No.
No. Remember that we can only reduce things when they're a factor. So this I could reduce because it's multiplication in my denominator. So it's going to be the same thing here. I can't separate those or reduce things when I have addition or subtraction in my denominator. Does that make sense? Now, that's a really common mistake, so just be careful with that. Now, if it's flipped, so if it's the opposite way, like if I have just one thing in my denominator and 2 things up top, we can switch that to be 2 separate. So what might we do instead? Again, kind of going through our list. Well, we can't factor it, right, because there's not anything in common. We can't convert to sines and cosines, because already sines and cosines. We don't have 2 separate fractions, right? But notice that one of our things is this middle one here is to multiply by a strategic 1. So think about just like with our, when I have to rationalize a denominator, like when I have radicals in my denominator, we're not changing the value of the fraction, we're just changing what it looks like, because we don't want radicals in our denominator. The same is going to be true here. I don't want to change the value, but as long as I multiply the top and the bottom by the same thing, I'm not changing the value, I'm just changing the way it looks. So what might we want to multiply to the top and bottom?
This might be going out on a limb, but I was thinking 1 plus sine.
I agree. Yep. So remember with our imaginary and our roots, we call this the conjugate when I just flip that middle sign. It is going to be helpful in this case because notice in our numerator I will have cosine of y times 1 plus sine of y. And then when I multiply out my denominator, I have 1 times 1 gives us 1. And then I would have 1 times a positive sign, which is sine. And then I have a negative sign times a 1, which is negative sign. Well, positive sign minus negative sign is 0. So that middle term goes away, which is why we want to choose the opposite sign in the middle. So that way those two things do go away. And then we have negative sign times sine is negative sine squared of y. So again, what do we notice about our denominator now?
It's a square.
It's a squared, and what do we usually want to use when we have something that's squared?
One of the identities.
One of the which identities? The Pythagorean identities. And if I look at my Pythagorean identities, I know sine squared plus cosine squared is 1. So how could I rearrange that to be what I have here?
Subtract sine from both sides.
Subtract sine from both sides. So what does 1 minus sine squared equal?
Cosine squared.
Cosine squared. Well, that's nice because now notice I have a cosine in the top and the bottom, and now this is multiplication in between my two things. So now we can reduce. So we're just left with 1 plus sine of y on top and cosine of y on bottom. So now what can we do?
Now you can split it up into 2 fractions.
Yeah, so now we are able to split it up into 2 fractions because notice I have my binomial in the top and then only one thing in the bottom. So we're allowed to say this is 1 divided by cosine plus sine divided by cosine. Well, using our reciprocal identity, what is 1 divided by cosine? Secant. And using our quotient identity, what is sine divided by cosine? Tangent, which is what we have on the left-hand side. So we can write our concluding statement. And our end proof. Questions on that? Yes, no, maybe? We all okay with that? Okay, let's look at our next example. Alright, so really we've covered a lot of these so far. We've worked with the most complicated side, we've converted things to sines and cosines, we've used our Pythagorean identities a lot, we've factored, we've multiplied, we found a common denominator, we multiplied by that strategic one. So then the last thing that we haven't really seen an example of is to factor out the rabbit, which one of the other pre-calc teachers kind of coined this, and so he likes to say it was like pulling the rabbit out of the hat. And what we mean by that is when we have something that has multiple terms, so like on this first one, notice that on the left-hand side I just have one term, right? On the right-hand side I have multiple terms. And what we mean by pulling the rabbit out or factoring the rabbit out is saying, okay, looking at my left side, I only end up with tangents. So tangent is going to be like my rabbit. That is what I want to pull out. So I would say, I'm going to start with my right side. And in this case, this is what I want to pull out. So I'm going to factor out a tangent squared. Well, notice that when I factor out a tangent squared, I get secant squared of x minus 1. Well, secant squared of x minus 1 should look vaguely familiar because it's one of my Pythagorean identities. And so what does secant squared of x minus 1 equal?
Tangent squared.
Tangent squared. So then I have tangent squared times tangent squared, which gives us what? Tangent to the fourth, right? Which is what we wanted in the proof. Okay, questions on that? Alright, so I want you to try the second one on our own. Okay, so it looks like several of us are most of the way there. So we want to start with the right side because our right side is the more complicated side. Now you could do this a couple of different ways, but I think the factoring the rabbit out like we done the last one is probably going to be the most straightforward way. So notice that if I look at the left-hand side, I have a cosecant, but we already have a cosecant by itself. We also have a cotangent though that's pulled out by itself. So then that tells us that that's what's going to be our rabbit, or that's what we want to factor out. So I'm going to factor out a cotangent, and then we're left with 1 plus cotangent squared of x. Well again, I have something that's squared, so that's going to be a good indicator that I want to use my Pythagorean identity. So what is 1 plus cotangent?
Cosecant squared.
Cosecant squared. Well, notice that we have a cosecant squared times a cosecant squared, which gives us cosecant to the fourth, which is what we wanted. So now we're done. Questions on that?
Wait, why did we stop at cosecant to the fourth times cotangent?
That's what my
Oh,
left-hand side is. So I've gotten it to be what I wanted it to be, so I know that I'm done.
Okay, yeah. See.
Alright, let's look at one last example. So I have cotangent squared divided by 1 plus cosecant of theta equals 1 minus sine of theta divided by sine of theta. So which side do we want to start with?
The left side.
Are we sure? Why the left side?
Because it has like the same amount of stuff on the right except it has a square.
Okay, sure. So let's start with our left side. So we have cotangent squared of theta divided by 1 plus cosecant of theta. So again, remember that because I have a binomial in my denominator, I can't separate these out yet. However, we have a squared in our numerator. So what is that usually tells me what I'm trying to do? So using my Pythagorean identity, what does cotangent squared equal?
Cosecant squared minus 1.
Now I still don't have multiplication here, so I still can't start just crossing things out. Because a lot of people just will be like, oh, now I have cosecants and lines, I'm just going to cross those both out. I can't do that because I'm adding and subtracting in my numerator and denominator. We have to make it multiplication before we can start doing that. We could, however, is there a way that I could turn my top into multiplication? So think about it like that instead. How can we turn x squared minus 1 into two things being multiplied together?
I forgot what like it's like specifically called.
Difference of squares.
Difference of squares. So notice that this would become x minus 1 times x plus 1. So we could do something similar here with my cosecants. So this would be cosecant of theta minus 1 times cosecant of theta plus 1. Well, now I do have multiplication. So now we are allowed to say I have 1 plus cosecant in the top and the bottom. So that just gives us cosecant of theta minus 1. Now, cosecant of theta minus 1 is pretty simple, yes? So it's hard to keep combining things or moving things around. Agree?
Mhm.
Okay. So this is an instance where, like I said, remember, these are not equations. I can't subtract 1 from both sides or multiply by something to both sides of my original. However, sometimes we might need to work with one side and get to a stopping spot and then work with our other side. So as long as you work with each side separately, we can work with them. You just can't do something at the same time to both of them. Because notice, if I start with my right hand side, well, here I do have just one thing in my denominator. So we can break this apart, and I have 1 divided by sine of theta minus sine of theta divided by sine of theta. Well, using my reciprocal identity, what is 1 divided by sine of theta?
Cosecant
Cosecant of theta. And sine divided by sine is going to give us 1. So notice that I didn't show that one side gets me to the other side, but I showed that both sides can get to the same thing. Does that make sense? So it's kind of like if A equals B and B equals C, then we know that A must equal C. Does that kind of make sense?
Mhm.
Alright, so we can still write our conclusion statement. So we can say, therefore, cotangent squared of theta divided by 1 plus cosecant of theta equals 1 minus sine of theta divided by sine of theta. And end our proof.
Will it ever not in the proof? Will it ever not equal that in the proof?
You mean like is there ever a chance that it will say verify the identity and it doesn't actually work? No. If it says prove the identity or verify the identity, there is a way to make it work. Now, if it says is the following an identity, then that could be a yes or no answer. But it's not going to tell you to prove something that's not true. It's not going to try to be true.